telescope all the way up so we climbed this telescope up like about the top. It stood on this plate at the top of this pole.
All right, we might get underway. Thanks for coming along to our main presentation night. And we have Mike, Dr. Mike Groth.
Cut out the doctor bit.
He hasn't got a stethoscope.
VK7MJ, MJ, who's come along to give us a talk on, well, the first one was listening to the planets. This is listening to the Earth. So we've moved slightly closer to home. So
Yes.
On that note, I'll hand over to Mike.
Okay, thanks, Justin. I hope I can do justice to the spin you've given in the previous news, the adverts. Yes, my talk tonight has been entitled Listening to the Earth, and it's a bit of a follow-on from Listening to the Planet. But Justin has sort of said that it's all about whistlers and lightning. Well, most of it is actually, because that was one of the more interesting things, and discovered that there's actually a hole in the ionosphere that VLF signals can go through, that in theory they shouldn't. So there is a wormhole. I'm going to note there's going to be no references to Alice in Wonderland and rabbit holes and trying to believe impossible things. I think I worked that to death in the last talk. But basically what I wanted to talk about, if I can work out how to... Yep. Okay. Seems to have been a slight problem with the formatting. Basically, the discovery of the Earth's natural VLF radio emissions, and these are basically audio signals up to about 10 kilohertz. And in order to understand them, you need to take a step back and look at the magnetosphere and the ionosphere. And then there's the thing called the Whistler mode, the wormhole in the ionosphere, a mode in which signals can travel along a magnetic field line through the ionosphere, right around along the magnetic field line, and pop up the other hemisphere and come back through the ionosphere again. And it's a very dispersive medium. And then I'd like to talk about an experiment done at Siple in the Antarctic back in the early 70s, where they actually triggered VLF emissions by transmitting from a very long dipole on the ice. That was done through Stanford University. Bob Helliwell, he was the real guru for whistlers and VLF work. Now, basically the first observations of natural VLF signals probably go back to about 1880, just after the invention of the telephone, with long telephone lines. Discovered they made whistling noises during thunderstorms and sometimes during aurora, but really the main body of evidence came from the First World War, because in 1915 the Western Front had basically descended to this line of trenches stretching from the North Sea down through France, and didn't move much more than about 10 kilometres for the next 3 years, but millions of men died trying to make it move. But the main method of communication was field telephones, and of course you don't go laying nice balanced 600 ohm lines in the middle of a battlefield which is being churned up regularly by artillery, and anyone who sticks their head out of the trenches gets shot. So they used earth return telephones, and of course the French discovered that there's these new things called triode valves which would amplify, and they could actually pick up the leakage current from the earth return up to about 3 kilometres away. And considering the lines were often only a kilometre or so apart, it didn't take long for the Germans to realise that, and then eventually the British did, because they realised that gentlemen do listen to each other's conversations. And of course most of them weren't gentlemen anyway. But really nothing much happened. There was no way of recording these signals. The only way of recording sound in those days was a mechanical phonograph, an acoustic phonograph. There was no way of recording electrical signals. So Heinrich Barkhausen, who made his name doing domestic ferromagnetic domains, he published a brief report in 1919 describing the various signals they heard. The German telephone interception services heard. But nothing else was done. Well, Germany in 19 was complete basket case. But in 1925, Thomas Eckersley, the British engineer, he published a bit more of a comprehensive review, and he did some observations, but I can't find any evidence of what he did, whether he connected an amplifier to just a wireless aerial or he actually did earth currents. But he did used a few tuned circuits and did some spectral analysis, and basically came up with three types of signals. The short pulses, and then there was the spherics, which are basically lightning strike static crashes, and yet that's earth currents. But there's these tweaks, and they look like lightning strikes with some frequency dispersion in them. But there were no frequencies below about 1.5 to 2 kilohertz. But the really interesting ones were the whistlers. And you can hear why they were called whistlers. They sounded like an incoming shell, or the German people apparently had the expression, you can hear the grenades flying, except of course there wasn't a bang at the end of it. But they went down about those 200 or 300 hertz. And then there was another one which sounded like birds, and they called it the chorus. And it sounded very much like the noises birds make in a rookery about sunrise, and they tended to occur just before dawn, and it was more common when there was a geomagnetic disturbance on. But really, nothing much happened after that. 1925, there were a lot more interesting things. There was broadcasting, there were valves, there was a whole new world of shortwave transmission. This was just a completely uninteresting topic.
And now was something completely different.
And thank you to John, please. Yes, we take a step back, a big step back, and look at it, because it all really connects to the sun. And the sun's basically a giant ball of plasma, about 1.5 million kilometres across. Centre of it's a giant fusion reaction, surface temperature of about 6,000 degrees Kelvin. And if you look at the sun, occasionally through a telescope, I don't recommend you doing it, Galileo almost set himself blind when he did it in 1610, but occasionally it looks nice and clear. Where's the occasionally it looks nice and clear, but most of the time it's got spots on it. And it's active, and sunspots usually occur in pairs, if you look carefully, because it actually ends the magnetic field lines. But they look like cold spots on the sun. But since about 2000, there's actually been dedicated satellites monitoring the sun, and this is from the SOHO satellite back in 2002. And if you look at the visible disk, you see a disk about 6,000 degrees Kelvin, and the sunspots look dark. But exactly the same thing photographed at 30 nanometers, which is basically 20 times shorter wavelength, so it's 20 times higher energy. The sunspots are actually very bright. They're about 100,000 degrees Kelvin. So the sunspots look dark because they're actually emitting large amounts of high energy ultraviolet. So the sun emits a lot of ultraviolet, and the ultraviolet flux goes up and down with the sunspots over about an 11-year period. And of course you all know that. You can also see there's a bit of some of the corona, some of the gas, very hot gas coming off from the sun, well actually plasma. And if you look at the sun during a solar eclipse, you can actually see the corona, which goes out about 3 million kilometres in diameter, and that's spewing out a mass of plasma between about 300 and 500 kilometres a second. It's mainly electrons and protons, because the sun's mainly hydrogen, but there's a few alpha particles which are helium nuclei, because the sun's about 20% helium, because the hydrogen's being converted to helium to drive it at several thousand tonnes a second, and it's got an embedded magnetic field in it. And this solar wind actually comes out and travels down the sun's magnetic field and forms like a big disk spreading out in the ecliptic plane, which is being twisted around, and it's pretty turbulent, and we call this the solar wind. And sometimes it's a gentle breeze and sometimes it's a violent storm. Now, fortunately, the Earth, which is the third rocky planet out from the Sun, is the only one with a significant magnetic field, which is really good because it shields us from the solar wind. Without it, a lot of our lighter components of the atmosphere would be blown away. We'd be like Mars with very little atmosphere, because it's not. And Venus has only got a very dense atmosphere because all the lighter components have been blown away by the solar wind. But when the solar wind hits the Earth, which has basically a dipole magnetic field, the solar wind is deflected around the magnetic field, doesn't like going across it, tends to squash it a bit on the sunlit side, on the day side, stretches out actually down to about 100,000 kilometres on the night side. There's quite a long tail with a lot of plasma sort of circulating around it. It's like the wake of a ship, basically. But here, between where the field lines here are going and the others that go out and get swept away and mingled with the magnetic field and the solar wind, there's a thing called the polar cusp, and electrons can spiral down that cusp along the field lines, and they land up in the atmosphere and cause the aurora. And the aurora concentrate in an oval around about 75, 79 degrees geomagnetic latitude. And the important thing is that inside the auroral oval, the magnetic field lines are open. They get tangled up with the interplanetary magnetic field. Here, between the auroral ovals, they're closed, because if you go back to school, all magnetic field lines are continuous. But yes, these ones are continuous, but they tangle up with a bigger magnetic field. And because that magnetic field is closed and the poles are stronger than out here, they trap particles. And there's two radiation belts that we didn't suspected were there, but we didn't really know until 1958 when the first American satellite went up with a Geiger counter on. And they called the Van-Allen belts because he was in charge of the project. They go down to about 500 kilometres from the Earth's surface, and they go out to about 50,000 kilometres. The inner one's full of protons and a few alphas, the other one's full of electrons. And actually they're quite intense magnetic fields. Fortunately, the International Space Station is down below the magnetosphere. If you were out up here, you wouldn't go for a spacewalk. You'd actually get quite a substantial radiation dose. Now, in 2012, they launched a couple of satellites, the Van-Allen probes, and these go round and round in the inside the magnetosphere, and they're in a very elliptical orbit, so they come down to about 500 kilometres and go out to about 50,000. And they discovered there's actually three radiation belts. There's the proton belt here in the middle, the electron belt, and then there's another belt which fills up when the sun's fairly quiet, and when you get a solar storm of some sort, or a solar mass ejection, that gets swept away down into the tail, comes down to the ionosphere, and you get a geomagnetic storm, and massive aurora, and power grids go funny, and all sorts of things happen. There hasn't been a really big one since the 1860s, and the reason they look at the space weather these days is because one these days would probably take down a lot of the world's power grids unless they could see it coming and shut them down in time. They only did shut them down for an hour or two, but otherwise it would literally burn a lot of transformers out in the system. Now, between the atmosphere and the magnetosphere is the ionosphere, and this is where it really gets interesting. Because the ionosphere is caused by ultraviolet radiation from the sun. It's high energy, it can knock an outer electron off the atom, so you've got a free electron floating around, you've got a positive ion, doesn't matter if it's an oxygen or a nitrogen ion, and sooner or later the electron will probably meet up with an ion and recombine. Any old ion will do it, doesn't have to be the same sort that it came from. Now, if you're way up in the top of the ionosphere, around 500 or 600 kilometres up, there is so little gas there that it takes many hours on average, for an electron to recombine. But if you're down around 60 or 80 kilometres up, can only take a few seconds for a recombination. So what happens is that as you come down, the electron density keeps increasing because it's meeting more and more air, and then by that stage some significant part of the ultraviolet radiation is already being absorbed. Although the atmosphere is getting denser, the actual ionisation drops off by about 50 kilometres, about the height of the ozone layer. Unfortunately, the ozone layer has got a very high ultraviolet absorption, and at night this disappears because it recombines, but up here at the F layer only about a third of it will about 2/3 of it will disappear. But there's this band of ionisation. I don't want to talk about the layers of the ionosphere because, you know, that's a whole different subject. But the ionosphere is this plasma cloud of intense ionisation surrounding the Earth. And these electrons, it's a bit like social distancing. They're all repelling each other, but they've got mass and they've got a natural resonant frequency. And the denser you make the electron cloud, the more they jostle. If you get a group of people together and you get more and more in the same space, they move about a bit more quickly. And so there's a resonant frequency, and if you think of the electrostatic charges as springs and a mass, you can calculate this equation here, calculate a resonant frequency, and if you put all those numbers in there and divide them by 2 pi, you'll end up with a number like 8.98 million. And if you look in the RSGB or the ARRL handbook or any of the radio handbooks, it'll tell you the critical frequency for any layer in the atmosphere is 9 times the square root of the number of electrons per cubic metre, and that's where the 9 comes from. For the ionosphere, at the peak of the F layer, that's somewhere about 3 megahertz in the very early hours of the morning, during the sunspot minimum in the winter, up to about 15 megahertz in the early afternoon during sunspot maximum. So basically the ionosphere, in theory, has this cloud of electrons. Now when the RF tries to go through them, the RF, the electric vector and the radio signal, tries to make the electrons oscillate. Now I've got my little probe here. I'll stand up for this because it's a bit easier to do. I just need to lean against the board here or I'll fall over. If I have a pendulum about 1 metre long, it's got a resonant period of about half a hertz. And if I try and excite it at many times its frequency, it really doesn't move much. But as I go slower and slower and slower, you get more and more absorption. But if I go really slow, until it really sucks a lot of energy out, but if I go really slow, the resonance really doesn't make much difference at all, way below the resonant frequency. So what happens is the electrons absorb energy, they vibrate, they re-radiate the energy, but they radiate the energy 90 degrees ahead in phase. And so what happens is the wavefronts actually appear to travel faster than the speed of light. The actual energy doesn't travel faster than the speed of light. And so the refractive index roughly starts off here at 1, which is the refractive index of the vacuum, and gradually gets down lower and lower and lower. And when you hit the plasma resonance, it goes to 0. And then it goes negative n squared. Well, of course, there's no real number, square root of a negative number. So basically, any frequency below the plasma frequency, it just can't propagate. So if you fire a radio signal up at about 3 megahertz up from at night, up the plasma frequency in the F layer above us here in Hobart at the moment, it's probably about 5 or 6 megs. And if you fire a signal at say 80 metres straight up, it'll go up until it reaches to the concentration where the plasma frequency is about 3.5 megs, and it'll come back. And that's what an ionosonde does. But the important thing is there's no propagation at all once you get below the plasma frequency. So in theory, you cannot get a signal through the ionosphere that's below about 5 megahertz, because it's going to, sooner or later, reach a level where it's going to be absorbed. But when we all know that you can fire signals up, and as you fire a signal up into the ionosphere, when it reaches the ionosphere, the concentration's higher at the top than it is at the bottom, and the ionisation actually speeds the wave up, so it bends over and refracts down. And we have all seen this sort of display where you get skip at HF, and there's a real art of predicting what's the best frequency to use to get to skip. But when you go to VLF, the wavelength's very long, and the plasma frequency over a wavelength, the refractive index, the electron concentration is going to increase over be at least sort of between 10 and 100 times. There's such a very rapid change in frequency, it doesn't bend, it actually folds the wave over, and you get total internal refraction, just like light shining on a prism or in a block of glass. And so the ionosphere, between the Earth and the ionosphere, acts like a waveguide at VLF. Now Marconi discovered this back in before the First World War with all his big spark radio telegraph systems. They were running at frequencies below 100 kilohertz. In fact, you got the best results below 50 kilohertz. And there were all these big alternators transmitting at frequencies of 20 or 30 kilohertz. And basically the Earth's like a giant waveguide. At the top, the ionosphere actually speeds the wave fronts up a bit, and the ground drags them back a bit because of the resistance. But between over seawater paths particularly, there's very low attenuation. A lot of noise, but in those days only using magnetic detectors and corundum detectors, the noise really didn't matter all that much. So, but the cut-off frequency of that waveguide, everyone who knows anything about waveguides knows that a waveguide, the minimum dimension has to be at least half a wavelength. That's the cut-off. Now for the D layer at night, it's about 85 kilometres above the ground, so it's a wavelength of about 170 kilometres. That corresponds to about 1.8 kilohertz. So frequencies down to about during the day it gets down to about 2.5, up to about 2.5 kilohertz. But basically frequencies above a couple of kilohertz can propagate very nicely. In fact, they propagate with very low loss. Now, by the time we discovered this, Barkhausen decided, well, whistlers were probably multi-hop signals from lightning strikes. And it turns out that if you do the calculation, for a signal that's travelled 20,000 kilometres around the Earth from the longest path you can get, takes about 70 milliseconds to get round at the velocity of light. But as you go below, if you get down to, that's that first octave above the cut-off frequency, there's a very rapid lot of dispersion. The frequency, it starts bouncing in very tighter and tighter waves, at tighter and tighter angles, and the delay between the high frequency and the low frequency is about 75 milliseconds. So the tweaks are really lightning strikes that have come under the ionosphere over a long distance. And the longer the tweak is, the longer the distance. So it propagates a long way, so you can hear lightning strikes on the other side of the Earth. But what about the whistlers? They've got delays of seconds. So Thomas Eckersley said, well, it looked at Edward Appleton's work when he discovered the ionosphere or proved its existence and did the mathematics, that it should be possible, if there was a plasma out here on the magnetic field lines, that it should be possible for a signal to travel along a magnetic field line, way out here, could be up to 100,000 kilometres and come down again. And this would be very dispersive, and this would account for the whistler. Well, the big problem was in 1937 there was a fellow called Adolf Hitler who was looking for peace, a piece of Poland, a piece of France, and a piece of Russia. And so there was a lot more important things to do, developing things like radar and getting ready for another war, because they hadn't really sorted the problems out the first time. So really nothing much happened until the 1950s. And in the 1950s there was a real revolution. There was the magnetic tape recorder was developed. been developed. There'd been magnetic recordings since 1898, and there'd been wire recorders and still band recorders used in the 30s. But it was the development of the tape recorder in Germany using paper tape coated with an iron oxide, and I think it was just lacquer on the paper tape, so it wasn't particularly serviceable. But of course the Americans brought the technology back, and 3M company developed the polyester tape with a magnetic coating, and lo and behold, you now had a method of recording sound. It revolutionised recordings, because previously almost all gramophone records were recorded live, cut straight to a disc. Here you could actually record them and edit them and do all this marvellous fudge. Now of course you can do it all in software. But the magnetic tape recorder was a real quantum leap in VLF work, because you could record signals, and when you could record them you could analyse them much better. But in 1953, a fellow by the name of Llewellyn Robert Owen Story, I think he always knows known as Owen because a lot of people can't pronounce Llewellyn very well.
Llewellyn. I'm Welsh.
Yeah. He confirmed Eckersley's theory. He did a whole pile of experiments. He used a tape recorder, and he had about a 10-channel set of filters, and he sent the signals to neon globes and recorded the data on a magnetic film, because that was what you did in those days. So that's technology. But the big problem is that renewed interest. There was obviously a plasma field surrounding the Earth. And this might be a method of actually probing it and measuring it. But how the hell do you get a VLF signal through the universe? Or as a certain person used to say, why is it so? And the reason is that the Earth has a magnetic field. And a charged particle reaches a magnetic field, it can travel along the field, but if it tries to go across the field, it goes round and round in circles. So what usually happens is the magnetic particles, they spiral along a magnetic field, and as they get to the point where the field gets stronger, the pitch angle gets shallower and shallower, and eventually they reflect and come back. So these electrons are bouncing back and forwards along the Earth's magnetic field at speeds of several thousand kilometres a second. They're radiating energy, and I'm afraid it's played havoc here with the formatting, but basically for electrons the frequency depends on the charge, the magnetic field and the mass, and divided by 2 pi to turn it into a frequency. For electrons it's 28 gigahertz per Tesla, and a Tesla is about the magnetic field you get in the middle of an MRI machine. For protons, which are 1853 times more massive, it's only about 15 megahertz per Tesla, or about 1.5 kilohertz per Gauss. Now, up in the magnetosphere, that means that in the ionosphere at the equator, electrons have got a gyro frequency around about 700 kilohertz. Above us at this sort of latitude, it's about 1 megahertz, and at the poles it's about 1.5 megahertz, because the magnetic field at the poles is about twice what it is at the equator.
What am I suggesting to you all? That to understand the behavior of nature, one must learn some mathematics, which is not only good for the mind and the spirit, but for the soul.
Well, yes, and he also kept telling us that there was a glass and a half of milk in every half pound of chocolate. But the mathematics, well, this looks a bit complicated, but really this was Edward Appleton's equation for the refractive index of the ionosphere. And if you ignore the magnetic field, you just get 1 minus x, which is the plot we did before. But you'll notice there's a y term for the magnetic field. That's the ratio between the gyro frequency and the signal frequency. There's a z term, which is depending on the number of collisions it makes. And there's an I in front, so that's a loss term. But you'll notice it depends on the transverse, and there's longitudinal. There's not just, there's a plus and a minus sign. The ionosphere doesn't have 1 refractive index, it has 4. It's quadruply refracting. If the signal is travelling along the magnetic field line, the electrons, if you look up the field line, they're actually rotating clockwise. If the radiated signal is going up the field line, it depends whether it's right or left-hand circular polarisation, because that'll interact differently with the electrons. If it's coming across the field line, if the electric vector is vertical, it'll try and move the electrons up and down along the field line. Well, the magnetic field line doesn't have any effect. But when you move it crossways, they want to go round in circles. So there are 4 refractive indices. And it turns out that when you get below the gyro frequency, one of the 4 solutions actually has a real result. And if you plot the refractive index against the frequency from about 10 kilohertz up to about 100 megahertz, say for the ionosphere above us at about this time of night, out here above the plasma frequency, the refractive index is somewhere between 0 and 1, or n squared, somewhere between 0 and 1, so that's real, it propagates. As soon as you get below the gyro frequency, n squared is negative, can't propagate, it's not real. But the L plus route, lo and behold, when you get to the gyro frequencies, a resonant goes down to an incredibly large negative value, pops up to a very large positive value, and then you get this slow signal. N squared is much greater than 1. There's this slow wave, and the peak velocity occurs at half the gyro frequency. And what's really happening, seems to be happening, is that because it's below the gyro frequency, a large, and the wavelengths along a large number of electrons are being spiraled. The actual field line's trying to track, they're trying to move the field line, and so there's this actual plasma, circularly polarized plasma wave travelling along the field line. And that's the phase velocity, but it turns out the energy propagates at about a quarter of the gyro frequency. But you'll notice it's only travelling, even at the peak velocity at a quarter of the gyro frequency, at about 6.5% of the velocity of light. So it's only travelling here about 36, about 3,500 kilometres a second. Not 300,000. It's 66618, about 18,000 kilometres a second. It's quite slow. But when you get down to very low frequencies or high frequencies, it travels even slower. It's a very slow wave, and it's very dispersive. But no frequency higher than the local gyro frequency can propagate. Now what happens, that means is that if there's a lightning strike up here, frequencies up to about a megahertz can actually penetrate. If they are close enough and they can couple into the magnetic field line, they can transmit through the ionosphere. And as they come out here, if that field line has an above average concentration of electrons, it's a bit, I was thinking of paraphrasing Animal Farm, all field lines are equal, but some field lines are more equal than others. It's a bit like money, it's supposedly everyone's equal, but some people got more money than others, and tends to stick to the people with the money. Well, it's a bit like that in the magnetic field lines. If you get an enriched magnetic field line, it acts like a wire, but it's very slow. The signal's travelling up here at only a small fraction of the velocity of light. And gradually the higher frequencies get lost, because out here at about 4 times the Earth's radius, the gyro frequency is down to about 20 kilohertz. So basically only frequencies less than about 20 kilohertz will get through to here. And then as it goes down again, eventually it'll get to the ionosphere, tunnel through, and then because of the very rapid, it's a very high refractive index, it drops quickly, it spreads out like a diverging lens. So it acts like a funnel at this end, funnels it up the field line, and then comes out and spreads out again. So you can hear the whistler, the gyro, if that lightning strike within about 300 or 400 kilometres of that particular duct can get up, and you can hear it within about 500 kilometres of the duct at this end. And the frequency delay is about roughly, time delay is roughly the inverse of 1 on f, root f of the frequency. But the actual ratio gives you information about the electron content. Now, one of the really big boosts to Whistler research was the IGY. Who can remember the IGY? Yeah, right. I gather it was actually initially organised by the United Nations as a way to get worldwide scientific cooperation. It really wasn't possible till after Stalin died in 1953, because Stalin was a trifle paranoid. And a Soviet scientist, if he even thought about communicating with someone from the West, he had a very short life expectancy. But after he died, things opened up a bit, and so it was a really good chance to do some worldwide geophysical research, because a lot of work needed worldwide research. It was an enormous boost for Antarctic exploration. It was the first successful trans-Antarctic crossing since Shackleton's attempt back in 1914, and also another world first. Edmund Hillary and a crew drove 4 Ferguson tractors to the South Pole because the Kiwis knew a good way to had to do it on the cheap. There were no real vehicles for that sort of work in those days, so yet 2 of them are still in New Zealand. It established international seismic networks, so we actually started to really understand what was happening in the Earth's interior. But it established a worldwide network of VLF listening stations, and these stations were really very simple. They were just a loop of wire about 5 metres square, about a 7 metre pole, about 20 metres of the old 2-core lighting cable you put up in your roof in the days before you had to put a 3rd core in. You'd lay it on the ground, put it through a transformer, a low-pass filter to cut out everything below about 20 kilohertz, into an amplifier about 40 to 60 dB gain, into a tape recorder with a clock to give you some time pips. And quite often they'd use 2 loops at right angles to each other, so if you did it in stereo you could actually look at the phase relationships and work out the direction. You can do it with just a short whip aerial and a high impedance amplifier, but this gives you a better signal to noise ratio, and you get some directional information as well. And there were 51 stations listed in Helliwell's book Whistlers and Related Ionospheric Phenomena, and that became the textbook published in about '68. That was the sort of textbook about whistlers. Bob Helliwell was really the guru. Graham Ellis here was a major contributor to the work, and Dick Dowden, one of his students, took it over to Otago, and of course he was my supervisor over in the early 70s.
Was station, Hobart Station?
Yes, there is actually. There's a station in Australia. There was Hobart, Adelaide and Brisbane. There's one at Macquarie Island, and I suspect there probably still is. And the interesting thing with Macquarie Island is that was the opposite end of the field line to the one in College in Alaska. There was a place called Unalaska out here on the Alaskan Peninsula. It was the magnetic conjugate of Dunedin and Lauder in central Otago, and I worked there in the late 70s around the satellite ground station. Wellington was a major centre in the 50s. Graham Alcock did that. And the other really important one was Siple down here, and that was where they did the VLF experiments I'll talk about later. And the opposite end of that is at a place called Roberval in northern Quebec. There was one at Santiago and one at Ushuaia. There was only one in Africa at Durban. There were quite a lot up in Europe, up as far as Greenland. But yeah, the 2 really interesting ones, as far as I know it, were Lauder and College. It's Lauder and Unalaska, and College and Macquarie Island. And having all this large quantity of data actually gave us some reasonable statistics. And this is a graph of the number of whistlers observed at Bird Station, which is 50 degrees geomagnetic latitude, and this is the number of thunderstorms within about 500 or 600 kilometres of its magnetic conjugate at 50 degrees north magnetic latitude. And you'll see there's a reasonable sort of correlation. This is a logarithmic scale, so it's actually a much sharper peak if you did a linear scale. There aren't too many thunderstorms in the Antarctic, at least as far as I know. Yeah, the relationship between thunderstorms and whistlers was pretty well established. But the interesting thing was there was a tremendous latitude effect. There were more whistlers observed in the southern hemisphere than there were in the northern hemisphere. There were virtually nothing observed between 30 degrees north and 30 degrees south of the magnetic equator, and virtually nothing after you get much above 70 degrees magnetic latitude. And the reason for this is pretty simple. The higher the magnetic latitude, the further out the field lines go. So in Hobart, which is about 50 degrees geomagnetic latitude, I know we're only 42 degrees geographic latitude, but because the magnetic pole is on the Australian side of the South Pole, we're a higher geographic we're about the same geographic latitude as Dunedin, which is 3 degrees further south than us, the Kiwis. We're one ahead of the Kiwis there. Macquarie Island is about 62 degrees magnetic latitude and goes out to a bit over 4 Earth radii, and the gyro frequency out there is only about 12 kilohertz right at the end of the line. At Siple, which is about 64, gyro frequency is down to about 6 kilohertz, and then as you get up to say about 70 degrees magnetic latitude, the field lines go out so far that eventually all these higher field lines never close. They get caught up in the solar wind. And so essentially the polar field lines aren't there because they don't close. So you've actually got to have a field line with some plasma in order to complete the circuit. When you get near the equator, the field lines are almost horizontal, and they actually don't go up into the magnetosphere. And the other thing is that in order to get a reasonable coupling, even at audio frequencies, your field line must be the refractive index of the atmosphere, of the ionosphere in the Whistler mode tries to push the wave vertical. But it's got to be within about 30 degrees of the magnetic field line to get any chance of coupling any amount into it. And so really, if the dip angle is less than about 60 degrees, you just don't get coupling into the Whistler mode. Now when you go between about 30 and 40 degrees magnetic latitude, there's the 40 degrees line there comes up. Between the 30 and 40, they go through the proton section of the magnetosphere. And so the plasma wave has to go through stuff which is much more massive. So the gyro frequencies here are between about 1 and 300 hertz. And so if you say at Brisbane and you hear whistlers, they are likely to have gone through the proton magnetosphere, and so if the gyro frequency is about 100 hertz, then the peak velocity is going to be about 25 hertz. The low frequencies you're not going to hear, but you will hear the higher frequencies. So what you heard there was you could hear the, let's go back one, let's see. You hear the fastest one, and then you hear the higher frequencies that are arriving slower. So it seems upside down, but proton whistlers aren't all that common, but they're only observed at between about 30 and 40 degrees magnetic latitude. Now, when the Whistler signal travels up along the field line and reaches the ionosphere at the far end, there's going to be a very rapid increase in the electron density as it gets to the far end, and a lot of the energy is going to be reflected back, and you get multiple whistlers. Now I've heard 2 and 3 hop whistlers on the ground, but that's 50 years ago, because my room was right next to the receiving section, and the loudspeaker was on most of the time, so I used to hear these things in the middle of the night when I was busy doing other things. So basically what's happening is that you get a lot of multiple reflections. I couldn't find any ground-based multiple reflections, but these days there are satellites up listening for whistlers all the time, and they get a lot. And this is from the Van-Allen A satellite probe on the 11th of September 2012, only less than a month after it was launched. But what you'll notice is see the dispersion increasing with the multiple echoes. What you will notice is that sometimes the echoes are stronger than the original signal, and they tend to occur, that amplification seems to be around about 3 kilohertz. That plasma tube acts like a travelling wave tube amplifier because it's driven by the electrons spiralling up and down. You get a phenomenon known as cyclotron resonance, because these waves are travelling, less than 10% of the velocity of light, so they are travelling quite slow. And these electrons are travelling quite fast too. And if the Doppler shift from the cyclotron radiation from these is the same as the frequency coming up, then energy will be extracted out of the electrons into the travelling wave. You get amplification. And that discovery worried the US Navy a bit, because in the 1960s they developed this big VLF global navigation system, the Omega system, and there are 8 stations all around the world, and in theory submarines could navigate without having to come to the surface by comparing the phase from 3 or more signals. But what the US Navy was worried about, and I suppose the Russians as well, was that the signals from the Omega station might go up along the field line, come down in the polar regions, and confuse the navigation. Now, if you happen to be in a submarine trying to sneak up a channel and you're out by a couple of kilometres, the results could be pretty disastrous. And so the US Navy was persuaded by a group back in about 1971 to fund a pilot program that I was involved with, where they set up a station, a fellow called Harry Kuhn. I don't know who he was working for. It might have been Stanford University, but he tried setting up a transmitter in Alaska with I think a 1 kilometre vertical aerial tied to a balloon, and about a 5 kilowatt transmitter and a very large loading coil, and he was operating on about 5 kilohertz. And we were trying to receive the signals in Dunedin and at Campbell Island, where we ran an outstation, and I built a bit of equipment to be a contractor. That paid some of my living expenses. The university are great for finding ways to get money out of things. It wasn't really a great success. We heard a few signals. We didn't get any emissions because they really didn't couple very well from a vertical aerial into the field line. And trying to fly a balloon in Alaska in springtime, not a good idea. So the weather, it just really, it worked out. Yes, there's a possibility it'll work. So, but the definitive experiment was done at Siple Station, where I think Bob Helliwell persuaded the US government to let him build up a 19 kilometre horizontal wire on the top of a 2 kilometre thick ice shelf near the Antarctic Peninsula. And the opposite end of that field line is in northern Quebec at a place called, I think it's called Roberval, but it might be, that's how it's spelt anyway, but it's probably got a French pronunciation that I don't know. But basically, it was a 19-mile wire, and they put it up on a poles about 5 or 6 feet high, because you don't want, ice has got terrible dielectric properties. In theory it's an insulator, but I believe Siple is a place where it gets quite a lot of snowfall, about a metre or 2 of snow a year, which in the Antarctic's a lot of snow. But never melts, it just builds up and up and up. And eventually they had to keep raising the poles, and eventually the station, I believe they established in about 73, got crushed by about 79 because the ice just built up and crushed the station. And they built another one in the early 80s and carried through to 88. And the other big problem is being an ice shelf, it moves. There's a lot of differential movement. And I remember Dick Dowden saying he met Bob Helliwell at a conference, and he said, Bob, he said, great idea, he said, but how do you stop the wire breaking? And the answer is, what makes you think it doesn't break? And it turns out that they would get it all going, and they'd get maybe a couple of weeks operation, then the wire would break and they'd have to wait for the weather to be right and go out and repair it, and then they'd get another couple of weeks operation. It was a bit of a hit and miss, but they got an awful lot of information over the 15 years that the experiment went. And it's almost one of the longest, not quite the longest amateur radio aerial. I know one that was 132 miles long, but that was a ZL. Kiwis always have to have one up, don't they? That's ZL4OM, but that's another story, back in the 50s. They had, I think it was, there were two transmitters. There was a Zeus transmitter, the original one, which was 10 kilowatts. Then there was the Jupiter transmitter, which was, I think, 100 kilowatts, according to what I can find out. And it could go down to 1.5 kilohertz. How they loaded it, I don't know, or maybe they didn't bother because they did a lot of work where they did multiple frequencies. So maybe they just handled the reactance, made something with a, that could handle a high reactive load. And the receiving station was up here in northern Quebec at a place called Roberval, up near the Labrador border. And this is one of the more interesting results I managed to get off the web. And you can see here they were transmitting at 1.4 kilohertz. How low can you go? That's about the lowest frequency I know of people transmitting signals. And they were transmitting 2-second long pulses every 10 seconds. So here's the pulse transmitted. This is the pulse received in Quebec, and it's about a second later. Actually, no, it's about 2-second pulse, about a second and 1 3/4 seconds later. And you see it's triggered to emissions. And then there's the second hop received back, the echo received back at Siple, and you can see there's a third one back here. And then the second pulse, there's one hop with only one emission this time, 2 hops, and a weak third hop. And the same here, 1 hop, 2 hops, and a weak third hop. That's the only real decent, really good result I could find. But apparently they're still mining data out of it. There was so much information. There's still probably a few PhDs and a few papers being written on it, keeping people out of mischief and out of the pub, I suppose. And the other one that they heard was the dawn chorus. No one really knows what causes the dawn chorus. I read a paper by Bob Helliwell in the late 60s, written in the 60s, and tried to make sense of it. I know Graham Ellis here wrote a paper on it, and Dick Dowden wrote a paper on it, and they all talk about Doppler shifted radiation from electrons precipitating down the flux tube. But somehow or other you get electrons injected into out here, causes the thing to become unstable. Now that injection is probably due to the fact that as the Earth rotates, the magnetosphere rotates with it, and as it gets towards the dawn it gets squeezed, and magnetic field lines change, couple and uncouple. Some of the magnetic field in the flux in the tail, especially if there's a bit of a solar disturbance on, couples down into the ionosphere, migrates across with all the collisions and ends up here and makes it unstable. I suspect back in the First World War they probably thought they were bird brains up and hurt in HQ who didn't know their beak from the backside. Probably said it in slightly more earthy language than that in those days. But that's not the only emissions coming from the Earth's magnetosphere. You can actually hear the solar wind. The electrons, as they precipitate down the auroral cusp, they're oscillating, and the gyro frequencies are between about 2 and 800 kilohertz. And it's very hard to hear that on the Earth. It's almost impossible. You can hear it from space in satellites, and And in fact, it was discovered back in about 1972 with a satellite in lunar orbit, or confirmed, because when it went behind the moon, the signal disappeared. Now this is actually a time-lapse auroral photograph from Caithness in Scotland. I sped it up a bit so that the pulse of the aurora, but what's happening is that the electrons are coming down with high energy. They're suddenly hitting the atmosphere. You get Bremsstrahlung radiation, which I think is a German word meaning breaking, screeching to a halt type radiation. I'm sure Warren, who speaks German, can probably tell me.
Yeah, it's about right.
And it's what happens in an X-ray tube where you fire high energy electrons, and you usually try and hit them into a tungsten target so they stop really quickly and you get high energy radiation. But here they're stopping fairly gradually, between about sort of 80 and about 40 kilometres up in the atmosphere. So you get quite a lot of energy in the audio spectrum. But the gyro frequency for the protons is about 200 times lower, so it's between about 1 and 4 kilohertz. So you can actually hear the protons in the solar wind, the so-called auroral whistling. And yes, this is also the Caithness. It was a display that lasted all night. It paid a nice, slightly dynamic visual background. And believe me, there are people who got nothing better to do than sit and listen to all these strange noises, and maybe they indulge in a bit of fine malt whiskey, a single malt whiskey at the same time. They need to get a life probably, but that's basically the noises the Earth makes. So that's where I'll stop. And gosh, I just squeezed it in the hour too.
Any questions for Mike?
Yeah.
Yep.
The whatever the radiation is that's spinning around.
Yeah, the cyclotron radiation.
Right.
Yeah.
Now you're saying it's going at 6% of the speed of light.
The actual, that's the electrons are spinning at the speed, but the actual yes, the actual radiation is travelling along. If it's in the Whistler mode, in the Whistler mode, yes, it's propagating along the field line.
At 6% of the speed of light.
The waves coming up are travelling at about 6% of the speed of light. The radiation from the gyro frequency, probably it will be travelling along the field line about that too, but you get quite a rapid, because the sea is quite small, you get a much bigger Doppler shift. And the gyro frequencies, those electrons, are going to be generally lower than the frequencies coming up, because they're coming up the field line. So they're coming from a higher gyro frequency, coming from a higher field strength. But if the two happen to match, you get energy coupling from one to the other. And they've both got to be going in the same polarity. So it's only the Whistler mode, which is where the circular polarization is the same as the spin of the electrons. That's the sort of it's what happens in a travelling wave tube. They actually accelerate electrons along the magnetic field. They have a solenoid on them, create an actual magnetic field, and they put the waves near the electron gun, and they put a spiral to actually generate the slow wave travelling along the waveguide, and they match the velocities, and the energy is transferred from one to the other. I think they used to use them in satellite transponders because they were very wide band. I don't know if they still do. They do they? Yeah. There's no solid state equivalent these days, I suppose.
Oh, there is. Yes.
There is, yeah. But they were very wide band and high gain. And basically it's a similar process occurring, except the electrons are being generated by the electrons being trapped in the field line. They're going back and forth like flies trapped in a room, flying from one window to the other to try and find a way out. That's a very hand-wavy explanation, and I'm not an expert. I had the luck of working with the people who were, but they're all dead these days, so I can tell you anything and contradict it. But that's as I understand it. I think I fused a few neurons trying to actually work out how the Whistler mode worked, going through Appleton's equations and a spreadsheet and trying to actually find out, gee, it does actually work.
How did those people come up, back in the 30s with the formulas this long?
Yeah.
Without computers and so forth. How do
Yes.
How do they get the idea?
Well, I suspect they had a rather vivid imagination. They knew electrons spiraled around magnetic field lines, and Edward Appleton basically used Maxwell's equations and the laws of motion to actually calculate the motion of electrons, the interaction between the radio frequencies and the electrons. That's where the equation came from. And I suspect that they had suspected there was a plasmasphere out as far as back as Gauss back in about the 1840s to try and explain the magnetic variations there. He thought there's something conducting with electric currents flying around in the upper atmosphere that causing these changes in the magnetic field. Well, he was correct in a way. And these currents were induced, of course, produced by the solar wind. Yes, it wasn't easy. These days, whistlers are, not really very important because you've got satellites doing it directly. But up until the 1970s, or even basically the 1980s, you had to do everything. There were no really computers as we know it. PCs didn't come into existence until about 1980. When I was at the university, they were a big thing. You put punch cards into and came back the next day and discovered you'd made a programming error. Yeah, it's a pretty esoteric field. Yeah, yes, right.
I was going to say, has there been any practical application of this? This theoretical?
No, not really. It's a terrible way of communicating because it's so dispersive. But it possibly could have been a problem with VLF navigation systems, but of course they've disappeared. It's really just these days of an academic interest, but it's still one way. I think there's still people listening to whistlers, seriously, but I think most of the work these days is they actually listen to the my chap I went through the university is just retired, Neil Thompson. He at the university at Otago, he was doing a lot of work with looking at the VLF navigation or the Navy communication stations running at 10-15 kilohertz. The submarine communication stations and looking at the phase differences. It's really good for measuring. VLF is really good for synchronizing clocks over a long period because it's so stable. So you can actually compare the phase of. These days, of course, with atomic clocks, it's a bit easier. But it's still very good if you want a very reliable, stable communication network for synchronizing clocks. I think they still broadcast on 60 kilohertz from rugby in England, and the WWV broadcast, I think, at 60 kilohertz.
Germany ran a system. I don't know whether they still run it, but Germany ran a.
Yes, they still run that. This type of clock was called Funkuhr, and I think the radio frequency was around 78 kilohertz or so.
Yeah, well, some of these magic watches that always kept the right time actually had a receiver listening to these VLF signals.
Yeah, and I mean, it was so popular and so common that wristwatches, kitchen clocks, train stations, clocks everywhere just used that radio signal to keep in sync.
Yeah, it is actually that VLF Earth VLF waveguide. Of course, it's very popular with military people for talking to submarines, and they did get down, I think, to 60 hertz or something, 57 hertz or something. Some of these ELF systems, so they could talk to deep submarines, and the aerials for those were whole virtually whole power grids and megawatts being put in, but I think they gave up in the end. They caused so many problems. And the data rate was sort of a fraction of a bit, a fraction of a baud at those frequencies. It was really very, very difficult to radiate signals down that low. Yep.
Sorry, probably unrelated, but being of a certain age, I remember listening to long wave radio back when I was a kid.
Yeah.
I mean, similar sort of thing. Is it the same phenomenon that's causing long wave radio to have that whistling sound as well, or is it similar or different cause?
Can't answer that. No, the frequency would be too high. That's probably heterodyning between another station.
Yeah.
The other thing is that I know there was the Radio Luxembourg effect, where Radio Luxembourg was so powerful it actually drove the D layer in the ionosphere past its linear limit and it actually modulated onto other signals. And there is a thing called HAARP, High Altitude Atmospheric Research Project or something, where they've got these VLF, these low frequency arrays, and they pump megawatts up in to try and modulate the frequency of the ionosphere. Yeah. I don't know much about that. That's a whole different subject, yes?
They're using it to, they cohere the signals, but they're slightly different frequencies, and so what they're able to do is create some structural friction, I'll call it, and they're generating heat at high altitude. The idea is to try and change the weather and do a lot of other things. Very interesting. There's a whole bunch of information now about modulating that level of the atmosphere.
Well, the attenuation in the D layer, and there's a C layer too, the attenuation is very high, and the attenuation goes up as the square of the wavelength. That's why, you know, broadcast should never get skipped during the day, because it's got, although it can reflect off the E layer, it's got to get through the D layer first. It's like a wet blanket. And at night it disappears, so you can get DX at medium frequency or along the grey line. But the moment you get daylight, well, the lower ionosphere is still like a wet blanket. So yes, you fire signals up at a few hundred kilohertz, it's going to heat it up nicely, which is I think where the Radio Luxembourg did, because they were transmitting like about 180 kilohertz or something like that.
Yeah, of course they used to use 16 kilohertz for the rugby radio.
Yeah.
Which, you know, in my time, you know, used to be sending out Morse.
Yeah.
And you could hear it running.
Well, the very famous recording on the album, on the one, was it Pink Floyd? I think it was, there's an album which, if you get the original recording and you do a little bit of signal processing, you can hear rugby.
Right, yeah.
Because the studio wasn't that far from rugby.
Yeah, rugby was on
16.
Yeah, something 16. That was actually the very first transatlantic telephone service was, I think, single sideband on, I think, 16 kilohertz one way and about 18 kilohertz back the other way. I think they did a bit of scrambling. I think they broke it up, but it was actually single sideband back in 1912. And that was, but most of the telegraph system between Britain and the US was still long wave right up until the war, through rugby there. I think they knocked the rugby mast down about 5 or 10 years ago. That was an incredible aerial array.
This might be a question for Rex. Is this a possibility for a burst mode like meteor scatter modes for WSJ2?
I'm guessing a lot, but certainly you can get scatter from lightning.
Yeah.
And obviously a burst mode like MSK441 or MSK would be the way to do it. But I know people have tried, but I don't know of anybody being successful.
Right. Yes, well, certainly coupling a signal into the field line from a transmitter on the ground is not easy. Yep.
There's a good bit going on with earthquake precursors.
Yeah.
And I was wondering how that might relate to what you presented.
That could
We're
well.
looking at the continental shift piezo effect and disruption of the magnetic field lines, causing changes in propagation at different frequencies. So I've seen charts. I don't know whether they're true or not, or magic, but there is some indication about.
It's always possible. There are a lot of things that are possible that we don't know about.
Yes.
But we haven't actually found them. After all, most of the things we thought were impossible, we suddenly discover, certainly in science fiction they are. Now they all, in Star Trek, they can always shift halfway across the universe in the space of one episode.
Any final questions from Mike? Can we show our appreciation?
Right.
Grab a coffee and quiz Mike some more.
Pies, I think the pies are like